All right, so here we go in our next section. This is 4.5. This is application of trigonometric derivatives, extrema problems. So we're max-min problems. We're looking to maximize or to minimize something that's asked for in this question. So section 4.5, here we go with this one. The first question here says an isosceles triangle. We've got a isosceles triangle that has equal sides of 15 centimeters. Use calculus concepts to determine the largest possible area of the triangle. And so let's start off with the fact that we've got a triangle that looks like this. We don't know too much about it except that this is 15 centimeters. We should probably start to label this. So let's call this triangle ABC. And it's an isosceles triangle, which means not just side AB and side BC are both 15 centimeters. It also means that that this angle, call this theta, theta is equal to angle A. It's also equal to angle C because it's isosceles. We should note that the domain of this is the biggest that angle can be is it can be 90 degrees, right? It can be, well, it can't be 90 degrees. It has to be less than 90 degrees. So A has to be between 0 and 90. In this course, we're going to be working in radians. So therefore, we're going to state, therefore, theta must be strictly between 0 and 2 pi, not equal to. The smallest angle it can be would be just over 0. The biggest angle would just be just under 90 degrees. All right, so what we notice from here is if we are dealing with area, that means we are going to have to look at the height of this. If I bisect that angle B, this is a right angle. Bisected that angle B. And what we do know about relationship-wise is we know that, let's call this a point D. We know that there is this relationship between this angle and these side lengths. Well, we're trying to find this, the height of this triangle or the altitude of this triangle. We do know that this is 15 centimeters, is AB is 15, and so therefore we have this relationship that sine theta is equal to BD, which is the height of that triangle, divided by AB, which is 15. So therefore, BD equals 15 sine theta. So that's the first stuff we're going to start with here. Okay. Next, we're going to also look at, we need to look at the base of this triangle. We need to, if we're trying to find area is equal to half times base times height of this triangle, then therefore we're going to need to know something about AC. And therefore, in our little half triangle here, we do know something about AD. And so from that theta, we can say that cos theta is adjacent over hypotenuse. So it's cos theta is equal to AD over 15. And therefore, AD is equal to 15 cosine theta. The reason that we know that we're going to be working with AD and we're going to be working with BD is because of our formula for area is half times base times height. And the base of that is going to be 2 times AD, and the height of that is going to be BD. So those are the pieces that we're needing to identify and we're needing to work with here. So we start off with that. And now we're ready to go. Okay. So let's formalize all that. Let's write that down. So therefore, area is equal to half times base times height, or base times height over 2. Changing that into what we know, this is equal to half times. Now that base was going to be 2 times AD, which is 2 times 15 cos theta. And the height, 15 sine theta. So there's my area formula. If we simplify that a step, area is equal to 225 cos theta sine theta. Now, as with before, what we're trying to maximize in this question is we're trying to maximize the area. So therefore, we're needing to find the first derivative of that area. And we're going to then let it equal 0 because we're trying to find where it's equal to 0. A prime is equal to. All right, so a couple things that we need to do here. This is, so we now need our derivatives of trig functions, and we're going to use product rule. So this ends up being 225, the derivative of cosine is negative sine theta. Sine theta stays there. And because it's product rule, we're going to add that 225, 225. Cosine stays there, and then the derivative of sine is cosine. Clean that up a little bit. The common factor 225. We have 225 cos squared theta minus sine squared theta, just swapping things around to clean it up. If this is equal to 0, because we are wanting to find our maximum, we're wanting to find where the slope of this curve is equal to 0, so therefore we let a prime equal 0. Now we have divide both sides by 225, add sine squared to both sides, and we end up with sine squared theta is equal to cos squared theta. And as we've seen with this, if sine squared theta is equal to cos squared theta, that happens on the 45s or on the pi quarters, both with the signs being the same, but because when we square root both sides of this equation, we end up with sine theta is equal to plus or minus cosine theta. And if that means that the signs are either the same or they're different, so it's all four of those points. Theta equals therefore theta is equal to quarters, 3 pi quarters, 5 pi quarters, etc. But we noticed right at the beginning that theta had to be between 0 and 90, so therefore it had to be, theta had to be between 0 to pi halves. And which of these is between 0 and pi halves? Well, just pi quarters. So what we have is we have a prime, and let's draw our number line. Our number line is going to go from 0 to pi halves. Pi quarters is our critical number in the middle. We take some values to make sense in this interval. So if we're wanting to look at to see what's going on in here, is this plot positive or is it negative? So if we're trying to figure that out, we need to decide, okay, so pi halves would be in there, or sorry, no, it's not. Pi 6 would be in there. So what happens with a prime? If a prime is this formula here, we have 225 times cos squared theta minus sine squared theta. Cos squared theta at this point is root 3 over 2. We're squaring it. Sine at that point, we're squaring it. And when we do this subtraction, we get 3/4 minus 1/4. This is positive. This interval will be increasing. When we look at numbers between pi quarters and pi halves, for instance, between pi quarters and pi halves, erase your tools. Between pi quarters and pi halves, we have, for example, pi thirds. And if I do cos squared minus sine squared of that, cosine squared is going to be 1/2 squared minus root 3 halves squared. And because root 3 halves squared is larger, this ends up being a negative amount. And so we end up with that will be decreasing. So from all of that, what can we state? We can state that area is increasing when theta is between 0 and pi quarters. Decreasing therefore, theta is equal to pi quarters gives the maximum area. So we do know that theta is pi quarters, gives us the maximum area. We're not quite done with this question. It does ask to determine the largest area of the triangle. So therefore, area is equal to 225 cos pi quarters times sine pi quarters is equal to 225 times root 2 halves, root 2 halves, 25, 2/4, 112 square centimeters. Units on this. Into the context, that ends up being your maximum area is 112.5 square centimeters. Woo. All right. Number 2. So we have a ladder that we're moving horizontally around the corner in the diagram. So this is the view from above of a hallway. We've got a 3-meter hallway on this side. We've got 2 meters is your hallway width down here. And we've got this ladder or pipe or rod that we're trying to get down the hallway. We're assuming that we are carrying this through and we don't want to damage the walls. So we can barely scrape the walls and see what's the biggest length of ladder, what's the longest ladder that can fit around this corner. So we are trying to maximize this. Now notice that if I move that indication of 3 meters, if I draw it here and call this 3, and this 2 meters down here, if I draw it here, then we've got 2 similar triangles. That this angle here, theta, will be the same as this angle here, theta. So we've got two similar triangles, if we have that. We are going to call this L1, and we're going to call this L2. And we're going to define our ladder length is the sum of those. Capital L is a straight line because those angles are equal to each other. And we are assuming that the corner in this hallway is at 90 degrees. These hallways are perpendicular to each other. And so there we go. Okay, so looking at this upper triangle, looking at this with this width of 3 meters. From theta, there's your opposite. So we have sine theta is equal to 3 over L1. Just that L1 is 3 over sine theta. We can even call that 3 cosecant theta. So there's L1. What do we know about L2? What do we know what's going on in this triangle down here? We have that cosine theta is equal to adjacent over hypotenuse 2 over L2. So L2 is equal to 2 over cos theta, which we can simplify to just 2 secant theta. So putting that together, therefore, L is equal to is L1 plus L2, so it's 3 cosecant plus 2 secant theta. That's what we're trying to maximize, is the length of this ladder. And so we take L prime. L prime. So the derivative of cosecant is negative cosecant cotangent. So we end up with negative 3 secant theta cotangent theta. The derivative of secant is secant tangent. So therefore 2 secant theta is 2 secant theta tan theta. All right, so let's express these in terms of sine and cos. We've got negative 3, 1 over sine theta. Cotangent is cos theta, sine theta. 2 times 1 over cos theta, sine theta over cos theta. Just changing each of those reciprocal functions into sine and cos. And then we put this all together. We have a common denominator. Sine squared theta, cos squared theta. We're going to multiply that first term up and down by cos squared. Gives me negative 3 cos cubed theta. It's 2 sine cubed theta. Is equal to L prime. Now, when we make this equal to 0, keep in mind that the denominator isn't relevant. All that we care about is how we're making the numerator equal to 0. Algebraically, we can think of this as we've just multiplied both sides by sine squared cos squared. And so now we have 0 is equal to negative 3 cos cubed plus 2 sine cubed theta. Cos cubed theta, 2 sine cubed theta. If we want this in terms of one function, Let's divide both sides by 3. Sorry, let's divide both sides by 2. So we have 3/2. Let's divide both sides by cos cubed, and we have sine cubed theta, cos cubed theta. We have tan cubed theta is equal to 3/2. We have tan theta is equal to cube root 3/2. So if tan theta is equal to cube root of root 3/2, our critical numbers here, we have theta is equal to, if I decimalize that, let's just call it 0.85-ish for now. Also 0 pi/2. All right, so let's continue over here. But what's with our domain of this? What do we have for theta? What is theta allowed to be? Well, theta has to be between 0 and pi/2, right? It can't be 0 degrees. If it was 0 degrees, then you could have that's just not going to work. If we've got 0, it's less than theta, it's less than pi/2. Theta is 0, and theta pi/2 represent. They represent the ladder being parallel to the hallway, right? So at 0 degrees, the ladder is like this. At 90 degrees, the ladder is like this down the hallway. And so our angle has to be somewhere in between those. Represent. So at 0 and pi/2, we would say that those represent the ladder being parallel to a hallway. Therefore, our critical number is theta is equal to 0.85, the cube root of 3/2. Here's 0, here's pi/2. So somewhere in between here is cube root 3/2, which is 0.85. So at this point in this question, it now makes maybe a little bit more sense to just take some sort of value that's between 0 and 0.85, like 0.5. And we're going to take that and plug that into our equation. We're going to plug that into our L prime to see that what our sign does on that. And it's going to take us a few minutes. So take a minute here. Let's hit pause and see if you can figure out what the sign of 0.5 is. It positive or is it negative when we plug it into L prime? So hit pause and come back when you think you have found these. All right, so hopefully you found that this ends up being negative. This ends up being positive on either side of 0.85. Maybe you took something like 1 as a number that you're plugging into your calculator and determining the sign of that. Once we've done that, we realize and recognize that that tells us that this is decreasing until it gets to cube root of 3/2, and then it is increasing. And so therefore we can conclude, therefore, a maximum angle, sorry, minimum angle provide maximum ladder length. Therefore, theta equals 0.5. When we substitute into your calculator, make sure that you try this. Try to use the cube root of 3/2 in your calculations when we're trying to use a formula and then determine what L ends up being. So try to keep this as accurate as possible, and then therefore L is equal to 7.02 meters. All right, hope you enjoyed that. If you have any questions, please don't hesitate to ask those, and I will see you soon.